So we're going to do Huffman encoding. Huffman encoding is pretty exciting. And the reason why we're going to do Huffman encoding is actually pretty simple, okay? Here's what we're doing. So right now, one of the biggest things that I struggle with is I have too much information. I just have like so much information, I'm going to die. We want to be able to play Doom. Everybody wants to be able to play Doom at the same time. So I need to be able to have 1,000 of you see Doom at the same time. The problem with that is that I don't have any encoding that I can use right now. I just have to raw dog it. And that's all we're doing is we're just raw dogging the encoding because A, it's really, really fun. And well, why the heck not, right? I want it to work in a browser, but I also want it to work in the terminal. So we're going to think more about how the terminal works, and we're going to try to get them to work in both places. So I'm going to write my own custom encoder because why? Again, well, why not? And so the first thing, we got to make some observations, all right? One, we are setting down ASCII, right? But we're also setting down color. And the color is 1 byte. So this is really good to know, and the ASCII is 1 byte. So that means if it's something simple, if we're literally only doing 80 by 24, right? 80 by 24, that is going to be 1920 times 2, right? Because I have 2 bytes. That makes things hard, right? So that means we have to send down a lot. Color plus ASCII equals ANSI? No, it's not just ANSI. They are ANSI colors that are converted into a 1 byte color representation, and then we're sending everything down, right? Okay, so you get the idea. So that's kind of where we're at. And so what we did is we first started off by doing RLE. If you're not familiar with RLE, RLE is run length encoding, which effectively is very, very simple. If you have W, 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 D, W, you can run length encode this as 3W, 1D, 1W, right? So run length encoding is really good when you have really long runs of the same character. It's not good if you have a bunch of indistinct characters. So if you have like if you only have 4 characters, but it's like evenly distributed, it sucks, right? So there you go. So we're going to do something different. We're going to do Huffman encoding. Huffman encoding is actually not that bad. It's pretty easy to do. So Huffman encoding starts off like this. It starts off first, you have to have a priority queue of what's it called? Of all of your occurrences. So that means if I have all my occurrences like 1, 1, 3, 5, right? So here, we'll go like this. We'll go like this. We'll go A, B, B, C, D. If I wanted to Huffman encode this one and generate a brand new fresh table from this, well, guess what? It's actually not all that bad. It's pretty easy to do. So what I do is I first do the occurrences. So we got A is 3, we got B is 2, we got C is 1, and D is 1. Then when we do that, we need to combine them. So C and D, we take the 2 smallest ones and we combine them, which will have left and right, and now we have a count of 2. Okay, that's pretty easy, right? Here, let me go like this. C, D, with a count of 2. Now, that means then we wipe this out and we put in CD with the count of 2. And then we just take the next 2 smallest ones and we combine them. All right, so we take this, and now we have 4, and we have B. Pretty straightforward, right? Then we do it again. So then this thing is 4, right? And this is 3. And so then it would end up being something that looks like this. 7, we'll just call this one A. Whoopsies. I'll put A on the other side. Right, A, and then this one points to right here. Which means that you could imagine that this is 0, 1, 1, 1, 0, 1, which means that if I get 0, it is an A. So if we would re-encode this as this, we'd re-encode this thing as 0, 0, 0, 0, hold on. That's a 0. 1, 0, 1, 0, 1, 1, 0, 1, 1, 1. Right? So that's like massively smaller. By the way, I generally like Infected Mushrooms. I don't like this song. There we go. We'll move on from Infected Mushrooms. So there you go. So that's all it is. Right? Does that make sense? Yeah, I'm new to streaming. Come on, I'm new to streaming, right? If you only use a few bits for length to support RLE and non-RLE, it does better. I don't know what we're talking about here, but there you go. You also have to send the tables. Correct. You also have to send the tables. At some point, I got lost. I don't get it. It's pretty straightforward, right? It's pretty straightforward. You're just building up this. So that means if I start reading this and I have my decode table right here, I go like this. Okay, 0. I'm at the head. I go to 0. Oh, I'm at a terminal value, and it's A. Cool. A. I read the next bit. Oh, it's A. 0. A. Okay, yeah. Oh, I get a 1. I go down to this side. I'm at 4, but it has no terminal value. So I'm like, oh, so this isn't a real place. So then I go, okay, what's the next bit? Oh, 0. Oh, 0. B. Right? 1, 0, B. 1, 1. 1, 1. And then I go, oh, 0, C. So you just re-walk the tree once you've built it up. 0 is not a separator. You read each bit, and you walk down the tree till you hit the bottom. Every time you hit the bottom, you go back up. Prime, where the fuck are the capybaras? I don't know, Afor. By the way, I hear you're here. So I feel like you got to come hang out at some point. Okay, what are you doing here? Are you going to come to dinner? Count. Make the tree using count values. Decode the string and add to tree. Effectively. Yeah. Compression is magic. Compression is pretty magical. So there you go. So this is compression. This is what we're going to do. Not too hard to do. So I have an idea. I want to create a format that's really sendable over the wire. So this is what I'm thinking. The first byte... I'm thinking this. Hold on, let me put it this way. Every single Huffman node can be encoded in 3 bytes. Okay, 3 bytes. We technically could also make it 5 bytes, and 5 bytes might have to do. We may have to make it 5, but I'd like to make it 3. And so what it does is byte 1 is the like value. It's the thing. Byte 2 is the index into the memory region in which the next node is, that is its left-hand side. And 3 is the index into this memory region. Do you see where we're going with this one? Yeah, you should, you dirty dog. Right? Into this memory region where it's at. So there you go. It's pretty straightforward, right? So pretty easy, I think, to implement this. And that means I can also send this memory blob down really easily because it is a Huffman tree encoded into this, right? So this would be the value or the thing. So if it's a 0, I know that this thing is non-encoded. It's a node. If it's not a 0, if it's a 1 or bigger, then I know it is a thing. Yeah. Or I know it's a value if 2 and 3. If 2 or 3 are zeros, then I know that this thing is a value and it's value 0. Does that make sense? Yeah. A tree represented in an array effectively, but it's not a heap. It's not a heap. Right? Why would you send down the tree with every response? Maybe. I don't know, because if I do that, then it's 500 bytes effectively every single time. So I don't know if I want to do that. Very nice culture. Yeah, I don't know if I want to do that. Runner, thank you very much. I may want to keep a tree and recalculate it like every X amount of times. Right? How do you read raw bits? I just read the least significant bit. Doesn't the tree change with data? Sort of. Trees don't always... Huffman encoding doesn't have to change. Does that make sense? Delta Huffman? Are you going to use recursive Huffman where the tree is also encoded in Huffman? No. Though that is very interesting. I can't imagine Huffman encoding is very good for that. Recursive Huffman sounds really bad. In my head, it would be. Because I assume the tree is largely unique data. Do you believe Huffman? I know Huffman. All right, so there you go. So we're going to build that. Should be pretty simple, right? Hey, thank you. G Codes, I appreciate that. Let's go, G Codes. Thank you. Griffing, how is Brazil treating you? Good food? Good food. Things are good. Very, very good. Laptops with extra long battery life for Linux? Yeah, that's what I use. There you go. I'm happy with this. So we should be able to do that. I think I can do this. In fact, I think I could do this first try. I think I could do this first try. Right? All right, I guess I have some changes here. Let's see. Small changes to run Doom easier. So I made some small changes to run Doom really easy. So check this out. Check out this one. So now all I have to do is I made something called right. So let's see, where are we? Doom main. So to run it, I simply create a new program with the name, with the args, and with the writer, and the writer is a Doom writer, right? And then once Doom is ready, I can just start pulling frames. And so then I can create frequency buffers, right? And then I can actually calculate, say, the frequencies. And I can say, okay, here you go. Here's the frequencies. So check this out. So let's do the first 5 frames, and let's check out the frequency of it all. Right? There you go. So there's the first 5 frames of Doom. And here's the frequency of those characters, which is pretty interesting. There's 65 unique characters. There's 69 colors. The colors are very few colors, and then very large amounts of colors at the end. So if I go back and I do the exact same thing and I go up to, like, say, the first 9 frames, exact same things going on right here, right? You can see that there's, like, very unused colors and very unused characters, and then very common characters over here. And I don't even think the common characters have changed that much. Tilde, hat, comma. Let's see, what are the most common characters here? Comma, tilde, or a hat, tilde. So it's like the same stuff. Why is text so big, Grandpa? So you can read it, dummy. Sorry for the convenience. All right, so this looks pretty easy. So we have a frequency table. All I have to do is just calculate Huffman from it. I think I'd do this. In fact, prediction time. I think I could do it with 3 runs of the program. I think I could first try this with 3 runs. I love you, but I got the overtaking on the backside of a side address. People don't believe in me anymore. People believe in me. Ooh, people think that I could do this in 3 runs. Let's go. Let's go. Hell yeah, 3 tries, you got this? Yeah, I think I got this in 3 tries. Weather looks nice, weather's light. I'd say less than 7. You were encoding the data with Huffman, and the game works via a binary tree. Pretty simpler. I was here, you were here. All right. Shall we do this? We shall. We shall. All right. So I think the first thing I'm going to want to do is I want to create a node. A Huffman node, which will have a value, which is an int, a count, a left, and a right. Yes. I like it. No. Let's have the left to be a Huffman node and the right be a Huffman node. All right, there we go. We got this, boy. We got this, boys and girls. We got this so good. All right, we got a from value. We got a join, which is going to be A, B, Huffman. And we're going to return that out. So value is going to be value 0. Count is A dot count plus B dot count. left will be A, right will be B. Okay, everyone should be, hey, Compiling J, appreciate for that resubscribe. Everyone should be tracking along. I'm feeling pretty good. I'm surprised. Let's say I am surprised Pikachu. Huffman is easy. Now implement it in Rust. Your mom can implement it in Rust. All right. We got a from value. We got a join. Do I have anything else? I believe I have a frec point. I have a frec point. From frec. Right? That means value is going to have a frequency. I think this is pretty clever. Actually, a value should also only be a byte. Yeah, value should only be bytes. This is actually pretty clever, I think. So how a frec point works, a frec point is the index into the frequency byte array. So this is kind of, this might be a touch clever. We might be getting a touch clever. Effectively, a frequency has, a frequency has, I count the frequency of each byte, and then I have the possible points being every single possible byte, and then I put things that exist in the locations. I know it's a little clever, but that means I can keep track of these possible point counts really easily. And this allows me to have like a simple count array, but it also allows me to have an array of just only frequency bytes as opposed to the whole thing. So instead of 256, I only have, say, 10 or 20. You know what I mean? Okay. Pretty straightforward, I'd say. All right. I like where I'm going from here. Frec.count. Left nil, nil. All right. I do know that there is a Go priority queue. I just looked up this just recently. It is the world's, dude, they really, there needs to be a generic implementation. The Go priority queue implementation is actually crazy. It's like actually just crazy. So here we go. All right. Gives us, let's see, we want to pop, giving us the highest. We want the lowest, right? We want the lowest. There we go, priority queue. We don't need index. Have that, we don't need that. Yeah. We're gonna push, we just push it in. Pop it out, we don't need any sort of that. I'm just gonna keep all of this crap right here. Again, absolutely crazy, this code. Absolutely nuts. And I don't need update. We're not going to update any values. I'm just going to push and pop, people. Push and pop because I'm creating new. And my chances to get into the Go standard library just popped. My chance to get into the Go standard... Wait, what does that even mean, Lithium? All right. So this feels good. I think I have every part that I need. Now I just need the Huffman. And I don't know what I need. All right. I'm gonna have to figure out also how to do some level of compression, on this because it's not gonna work. Huff it up real good. Oh, we're gonna huff it real good. We're gonna do a really, really good job with Huffman. All right. So I'm going to say that Huffman cannot be bigger than 256 bytes because right now I'm having 1 byte jumps. I could technically do this different. I could add an extra layer of complexity, which is maybe not a bad idea. I'll do this after this implementation, but my first implementation is 3 bytes. But the other idea is that 2 and 3 are numbers between 0 and 127. And if your value 128... that just simply means we use values 127 or 0 through 127. So in other words, we use the 7 least significant bits along with another byte of bits for your length. So like your standard WebSocket kind of protocol right here. Kind of like a WebSocket-y thing. So that means I could have extended searching. So we'll do that afterwards. But right now we're gonna do that. Yeah? Does that make sense? You like that? I like that. We'll do that afterwards. But right now I'm gonna keep it as 256 byte maximum, which we should error then. We should error on real data, but we should be able to set up tests to kind of prove it. All right. So function. So I'll go like this. New Huffman is going to be. Do we even need this? I don't even know if I need this. So I'm just going to go like this. Yeah. Yeah. Everybody, the basis of all compression is the idea that data is not evenly distributed. That is the basis. You cannot compress equally distributed data. It's just not really. Yeah. It's like impossible. All right. So what I should be able to do is I should be able to go like this. Points equals make frec point, and then I want to go frec dot. All right. This should be the amount of different points I have, right? Length is, yeah, count. Okay, good. So that's how many points we have. And then I'm going to go like this. I'm going to go copy points, and then I'll go frec dot points. All right, so there we go. I have my own points. Do I even need to do that? I don't even need to do that, do I? I don't. I don't need to do that. I can just go Huffman nodes, huh? Yeah. And go, what is it? What's the thing called? Frec points. There we go. And go nodes I equals from frequency. There we go. So we converted all of our nodes into frequencies. Looking pretty good. Okay, so we take our frequency points, turn them into node points, and now we're going to start Huffmaning them by making a priority queue equals PQ. I don't even know how to create a new one of these. That's right. Oh, that's right. So if we do this, we actually want to go like this. Right? Which is a Huffman array. So we've created a Huffman array that is the priority queue. Right? So that means all we have to do now is just we're going to push all the items in, and then we're going to PQ it. So I'd go like this. Heap.init nodes. Yeah. This is looking pretty good. We're actually looking pretty good. Okay, so we got our heap initted. So now I'm just going to keep on going while. Dude, that's supposed to expand it. That's supposed to expand it to that. While the length of nodes is greater than 1. So we're going to, oh, not while. We just keep on going until we get all the way through. And now I'm just going to go like this. All right, so remember, this is what we're doing. Remember, we're going to be encoding it like this. Value, left index, right index. Yeah? So let's have a little encode function. Func. I think an encode function is a good idea. Func encode. Yeah. Yeah. Data. Let's see. Do I even need an encode function? I don't think I do. I don't think I need an encode function, people, right? I don't think I do, right? Welcome to Brazil. Yeah. Will he render the video in the terminal too? Oh, that's why we're doing this. I'm just going to assume it's going to be this. There we go. So I got my current index into the priority queue and this. We've created the heap. We've done this. So now all we have to do is just pop them 2 off at a time. Write them into the array. This is so good. This is so good. I can't believe how well this is going to work. I literally cannot believe how well this is going to work. So I need a way to encode. I feel like I'm missing something though. I feel like I need a recursive encoding. I don't think I need to recursively encode yet. I think I'm, you know what? Let's just build the tree before we build the encoding, right? Doesn't that sound better? Yeah. Right? Yeah. Yes. I think this is going to work out. There we go. So we just keep on popping 2, joining, popping 2, joining, popping 2, joining. And we're always grabbing the smallest ones. This is why priority queue works. Does everyone understand priority queues? Priority queues just always grab the smallest values or the largest values. How do you overcome this? By doing it a bunch. That's it. Be fitting Huffman. Be fitting these nuts in your mouth. You think I'm gonna fall for a D's nuts joke that obvious? You know the only thing you're gonna be fitting? What's be fitting? Be fitting D's nuts. Hope I could no go. Go's not that hard. Just push through. Yeah, come on, found out. No, it's obvious. It's too easy to see that one. Okay. So now I have this. So now I just need to encode the tree. Func, encode tree. So I'm going to go like this. We're going to pass the data. I'm going to go like this. I'm going to go count equals 0. And we're going to go like this. Count plus equals 2, right? Every time I pop off 2 nodes, it requires that. And I'm going to start off at 1. So effectively, I can say this. If count times 3 is greater than 256, it equals 256 or greater. I can go like this. Never had that problem in my life. You know what I mean? You know what I mean? Never had that one. Chadsby trying to run 2 IQ plays on Prime. Yeah, dude, come on, people, get your shit together, okay? All right, so let's go like this. I think there's a way to wrap join, so that means I should be able to join Huffman too large, and then I should also be able to do format dots. Do you guys like that? Judo, is this like proper error handling? Am I getting closer to proper error handling? Am I doing it? Am I getting close? It's a perfectly average size. Yeah, this is a very standard. Let me see again. So what I'm doing is I have my defined error that I export. So you can errors is. And then I also, when I join this error, I'm saying, hey, you have a Huffman too large. And then I give a more specific message of, node count exceeded, 256. Right? And kind of doing that. Yeah, that's starting to look real sexy there. Yeah, I feel like I'm kind of doing it now. I feel like I'm starting to get there. Smarts get your PR approved. Power gets your project buy-in. You think so? I think smarts get power buy-in too. Or Smarts gets buy-in. A smidge too big for a Huffman, even. I'm starting to kind of feel it. Received. Yeah, there we go. And so then I can just go like this, count. So I kind of know, like, oh, this thing's too large. Right? Okay. Let's go. Let's go! All right, so I'm going to go like this. I'm going to go count times 3. Count times 3, because remember, we're doing 3 bytes. I should probably make like a magic number. Var Huffman header. Huffman encode length. That makes it way too large. Makes it way too large, people. All right, so we're looking pretty good. We have our calculate Huffman. We got this one. We got our Huffman encode length. We got our max bytes. We created our data, and so I should be able to call it this. Encode tree, we should be able to pass in data. Encode tree is then also going to take in the index, which is going to be an int. Yeah, and it's going to return out, what does it return out? It needs to return out an int, because we're about to go recursive on this son of a bitch. Okay, so it comes in, and it's just going to start writing them out. So I'm going to go like this. It's going to look like this at some point. It's going to look like data, write index, you have to start with left index. There we go. Ooh, you know what we also want? I forgot about that, huh? By the way, here is like the recursive, the best recursive advice I could possibly give you. Don't do your base condition somewhere else. Think about your base condition first clearly, then the rest of recursion is simple. Okay? The rest of recursion is simple if you can formulate your base case well. I will not encode a nil object. That's my base case. I'm done encoding. That means all I have to do here is go like this. I have to encode the current data, which is pretty straightforward. I'll go like this. Data index equals node dot value. All right. Data dot index plus Huffman header encoding length equals, or not that, 1 byte is the left jump, right? So left jump. I'll go like this. Left index equals index plus Huffman encoding length. There we go. Is my left index. And then I do that. Now I have my right index. Then I encode the right index. Oh, I think this is right. I think this is so right. I think I literally have done this first try. I feel like I've done this first try, and it's so good. It's so good. Now we just pop off the last item in the heap. We popped off that last item in the heap, and then we just simply have to go like this. I think that's it. I think I got it. I think I literally just Huffman encoded. Yeah, that's easy. All right. Crow with knife. Wait, what is that? Wait, what is this crow with knife business? What's crow with knife? Crow with knife, D's nuts? Please stop the bot raid promoting meme coin. Oh. Crow with knife? Can someone add a banned term crow with knife? This guy's an actual real person though. That's the funny thing is this person's an actual real person. Why are you spamming and raiding other people's stuff? Typically, you're weak, Chimone. Hey, can you add a... Oh, just... You're stupid. You're stupid. Oh, man, you're like so stupid. Dude, imagine being that weak. Imagine being that actually weak. Absolutely pathetic. You can take it out of emote only mode. Dude, imagine being so weak that you have to advertise your shitty product on other people's channel. Absolute weak. Smooth brain. Like, the only way for you to get anywhere is by you spamming someone else's channel. And the worst part is that not only do you do that, that you go to someone else's channel and spam. Like, you have to be a pathetic piece of crap to follow somebody, right? You do. You actually have to be completely pathetic to follow somebody. Because it's the one thing, the person who's orchestrating it, I would consider them effectively like on the side of being, they're acting evil, right? But the people that are just going to people's channel and spamming, weak. Yeah, fuck that guy. Exactly. Weak. 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 All right. I think we got everything done. What are you doing in Brazil? Living the dream life? Small peepee. Small peepee. Anyways, you're weak. If there's any other individuals that are still trying to spam it and you're actually here by your own volition, just think about where you're at in your life. It's like bottom of the barrel, dog. I'd recommend like maybe Jesus. You know, maybe go hit church for a little bit, reconsider your life priority. Something different, okay? This is not good. Hey, thank you very much. Appreciate that. Igor Set. All right, so we are still Huffman encoding. I think I literally have this first try. I think I genuinely have this first try. Hold on, it's too loud for me. Okay, that's good enough for you guys, I think. There you go. All right, so I think this is pretty much everything I need to do. I went through all this, so let's do a quick test. I think the test should be pretty easy to do. Huffman test.go. So I'm going to test the Huffman. I'll have a frequency, which is a new frequency, right? And then I'm going to go frec.write. It's right? I think I kept it the same. No, it's not. What is it? Did I call it frec? Yeah, I think I called frec. Yeah, you frec the data. You frec the data. All right. So let's go like this. Let's go A, B, C, D. So exact same data that I produced last time. That should make things easy because we should have a pretty good idea of what we have to do. And for me to prove that I got this thing correct, I'm gonna debug print it. I think that would probably be the way to go, or I can return the data. One or the other, right? Yeah, oh my goodness, I'm sliding all over the place. Assert that index plus 3. There we go. My man is in the zone. Oh, yeah, we're going. Finish signalings. We're getting close. We're getting further. All right, so there we go. So we got this. Do a little negative space programming just to kind of assert to let myself know. So it's not just some like random index out of bounds, but instead it's like, hey, you've exceeded the size, right? Which is kind of nice, I think, to do. All right, so everything else looks really, really good. I think I got this, and so I kind of want to have a little bit of a debug. Okay, so let's go like this. Let's go like this. Func. Huffman node. Ooh, I like the song. All right, so to debug this thing, we gotta go like this. It's repeat, right? Yes. Get the repeat in there, so that means I go indent string, and then I got to do the actual value here, which is going to be h dot value. Beautiful. Absolutely beautiful. Oh, this is so naughty. This is so naughty. Look at what I've done. Look at what I've done here. Look at that. That is so naughty. I'm taking advantage of a horrible feature of Go. I shouldn't do this, but here we are. Do you see what I've just done? I don't know. Right? I don't know. I don't know. You know what I mean? It's pretty disgusting. Yeah. All right, I think that's good. I think I just wrote good debug code. I think we got it all. Let's go down here and let's go like this. Let's go like this. We ever head.debug. Yeah. Yes. Yes. Oh, yeah, that looks so good. Yes. Yes. Tell me that is not feeling good. Tell me that does not feel good. Why the function header has the type before the name? That's just Go. Wager first try attempt. We already have. Here we go. I'm feeling very confident about this. So let's go like this. I'm going to start there. It should print out the tree. If we've printed out the tree, then I should be able to just write out the tree. The problem is I don't know the order in which the tree will be created. So there is like a little bit of a funny kind of test to this. It should produce the same thing every time. I just don't know the ordering that it's going to be first try. But we should be able to see the printout that's correct. So if I've done this correct, then we've done this. Come on. Come on. I get 3 runs. Remember, I get 3 runs. Brazil? Yes, Brazil. I only get 3 runs, people. 3. Question. Can 3 runs for first try? Question. Does a run count if I just run the test? That proves that it works. What I mean by that is that I can run the test and then I get one run to try to fix it. I run the test, I get 1 run to try to fix it. I run the test, and if I fail, I fail. Okay, so you're saying, yes, it does count. Okay, I just wasn't sure if the feedback attempt sounds like that. So if it's like that, then that's fine. That just means that before we run it, I just have to put in logging in case I fail. Right? See, typically I wouldn't do this because I was like, oh, the run doesn't run. It would be, I get 3 attempts at making it correct. Right? Right? We forced him to do TDD. Yeah, effectively. Let's see. You got close to it. All right, we got length of our heap. I mean, I didn't want to have to do this, but here I am. Okay. Hey, it's not my fault. This is what you guys wanted, okay? So we're going to go like this, indent string, that. Perfect. All right, so I'm going to just... I got to be careful here. Okay. Sorry, I need all the information I can get out of here. I just need it. I think we got it, people. I think we got it. All right, there we go. There we go. There we go. We're gonna debug that one, and then I'm gonna encode tree, walk this down. Hey, I only get 1 try at this, okay? I only get 1 effing try at this, buddy. Can that happen? I don't know if that can happen. I don't actually know if that can happen. Right? Because I'm worried about this. I don't know if I'm going to get a nil or what's going to happen there. That's kind of like a, I don't know. What is going on? Is this extreme programming? No, it's actually so shockingly not extreme programming. Here, I'm going to like this. Node is nil. at Yep, all right. Oh yeah, there we go. Encode tree %s Let's go. All right, I think this should be enough. Okay. I cannot wait. I feel like that's cheating. I feel like that's cheating. Question. Do I get to rerun it to print out the output? Because I forgot an argument to the test. I say yes. Well, actually, I don't even care. I say yes. Because that's me. I think I got that. Ooh, see, dang it. I didn't add new lines, which really is screwing up my debug print. So I don't actually know if I got it. Damn it. Okay, so if I'm not mistaken, yeah, okay, so actually I did get it. I think I got it. Yeah, I think I got that. Yeah, yes, I did. Oh my goodness, I did, because that's D, that's C, that's B, that's A. Boys, we just Huffman encoded that first try. Let's go. Let's go. Let's go. Let's go. Let's go. I'm like 99.9999% sure I got this one. The only thing I have to do is just simply, yeah, because look at this. There's a heap length of 4. I have 3, count of 3. Yeah, that's right. So that's what it should be. There's D and C added. And then node has now length of 2. That's right. And so then I do it again, which is, it's going to be 2 and 2, which is going to be B and value 0, because this is a non-terminal node. It's going to do a thing of 4, which means I'm going to have 3 and 4, which means I'm going to have a node of 7. Like, this is it. And this is our head node. This is legitimately it. We just Huffman encoded the sons of bitches. We have Huffman encoded that son of a bitch. Okay, we did it. Am I missing anything? All right. So that means my next run, all I have to do is come up with the data array to properly print it out. You know what I didn't do, and I feel like such a dummy? I should have just went like this. Right? I should have just done that. I didn't, because I'm an idiot. I'm in Sao Paulo. And now I have this, and so now I have to like this require equal data. All right, so the data should be the head data. The head data should have, let's see. So I go left jump first, which should be 3, right? Because remember, it's header size. And then this one I don't know yet. Okay? Left should be left is A, right? We descend with A first, right? Yeah, we descend A first. All right, so that means that it should be A. That's the value. And then its left is is 0. It should be 0. It should be 0, 0 if I've correctly encoded nils. I don't think I correctly encoded nils. I think that's one thing I did not do correctly. I'm wondering about that, because I don't know if we initialize buffers with zeros or not. Hey, thank you, Joker Dan, for that tier 2. Let's go. All right. So if I've done that correctly, it should be this. And that means this thing should be a 6, right? Which should have a value of 0, because this is a transient node. which means its left should be at a 9. Its right is, I don't know what's at there. The 9 should be a what? The 9 should be 66, which is a B. Now, if I've done this correct again, remember, it should be 0, 0. Which means I should have 15 and 18. Ooh, I think it's D first. If I remember correctly, it's D first and then C. There you go. So that should be the proper Huffman tree. Left gets encoded, right does the jump, left gets encoded. So that this literally means that A should equal 0. B should be 1, 0. D, if I've done this right, should be 1, 1, 0. And C should be 1, 1, 1. Yeah? Yes. Yeah, the answer is yes. Huffman's a tough one. So if I've done this correctly, let's go back to this and make sure I have this nice, beautiful new lines here. All right, so whenever I do a nil, I do a new line. I do a new line here, and then these each do a new line themselves. Okay, so this is test number 2. I think it's going to fail. I have a strong feeling it's going to fail first try. But why not? Yes, okay, so it did fail. Okay, we did fail, but why? All right, so let's look at this. Okay, so let's see. Expected 036, 036. Good. 41, 00. 66. See, dang it. Dang it. I knew I had some 0 data in there. Oh, I should have used my run correctly. I didn't use my run correctly. Dang it. How did I not use it? See, it has 66. It shouldn't have 66 in there. It should have 00. It should have 00. Okay. That's me being a dummy. That's me being a dummy. Okay? That's me being a dum-dum. Okay? Because it should be the following. I have to pee. I'll be right back. I have to pee. I have to pee. No, hold on. You guys are gonna say I cheated somehow. You guys are gonna say I cheated somehow. I refuse to have you guys tell me I've cheated. I refuse. I will hold this pee-pee inside of me. No matter what. Screw you! Ah! I was going to say you cheated. I know you did. Okay. Whew. Okay, I know what happened. What happened is so obvious. What happened is so obvious. Effectively this. If... Oh my goodness. I mean, I could change my data also, but I want this. Oh my goodness. Because that's it. Everything else is correct, right? I got 41, 41, 6, 6. Yes, that makes sense. 0, 9, C, let's go. 42, C, C. Of course it is, because that makes perfect sense. 0, F, 12, 44, 12, 12, 43, 15, 15. Let's go. Oh my goodness, we got it. 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 Last run. I'm going to go P in victory. P in victory. First tried that son of a bitch. I just had data I didn't like. Got it. The name. You know the name.